Okay, just a tiny bit more about more advanced function components. We can get at different parts of a function using these functions. So body gets you to the body of a function. Formals will give you a list of the formal arguments of that function. Args will give the names and those default values. When you have a lot, this is really useful. Some functions have a list about 50 long of these, and it's good to see that printed out. You can also get that off the documentation as well, although poorly written documentation will not always be as thorough as this. Nargs can be used within a function, and it gives you the number of arguments that are currently supplied. So that's within a function. And similarly, match call is used within a function also. That's why these are separated out from those other ones here, and returns the function call in which those specified arguments are provided. This is more useful once you're starting to write more advanced functions to include in, say, an R package. Then you need to be very aware and be checking these arguments that are supplied and what the names are and so on. So let's apply all of this to do a simple simulation. So for a random sample, the sample mean, if n is big enough, is going to be normally distributed, and we can do something like construct a t-confidence interval. We've all seen this in our first stats course. This is something we like to be able to do, but the question is, how large of an n is really necessary, and how does the shape of the parent distribution affect how large n needs to be? Okay, so for example, if n1, x1 up to xn is from a normal population, then this is correct for any n. However, with a highly skewed distribution or even a somewhat discrete distribution, how large does n really need to be? If we're dealing with proportions, for example, how big does it need to be? So I often have my students investigate this in lower level classes by using some sort of automatic simulator, but we can write this within R. So here's some example code, and this will be provided to you online. This is just going to simulate this experiment to see. This is what we call a simulation experiment in statistics. Let's go over the arguments to our function, this sim.t.ci function. So here we get a random variable generator. So what we want for, do we want normal, do we want uniform, do we want exponential, do we want binomial, and so on. The sample size, it could be a vector if we're going to operate on different sample sizes all at once. The number of simulations, so how many simulated data sets are you going to generate? Your alpha level, default is 0.5 and default is 1000 for this, by the way. The population mean, and then other arguments that need to be passed into this random variable generator. So for example, with exponential, you need to pass in lambda. For the normal, you need the mean and the standard deviation. Okay, so first we're going to go in and verify our arguments. So stop if not. Remember what that is going to do is stop iteration of this function if certain things are missing. So if if anything is missing, such as the random variable generator, if it's not a function, if n is missing, or if mu is missing. Okay, so it's going to check that everything's in there. Results. It's going to set up the results so it's ready to be occupied. Then we're going to loop through different sample sizes. So if n is a vector, it's going to loop through all of those for the length of n. Okay, so first we set up our array, and then we do our simulation loop, and notice that's where nsim equals 1000 takes a role. We generate a unique sample for each of those n's. So in position 1 could be one sample size, in position 2 could be another sample size, and so forth. We calculate the sample mean. We calculate the lower limit. Notice that's using the correct value of n because n could be a vector we're allowing. And then we calculate whether or not the mean is captured. So if the mean is greater than the lower, but smaller than the upper, then we've captured the true population mean. Otherwise, we get a 0. So this will give us that true empirical error rate or confidence level. It'd be the empirical confidence level, wouldn't it? And then we get back for our results within the object results that recall was set up here, what that mean value for the CP is. So it's going to go through all 1,000 data sets, record whether or not the true mean was captured for that particular simulation, and then give the proportion of times it was captured. And that goes within that ith row of results. Then it'll return results. So let's run this one time. So let's see what we did here. We're going to use the normal distribution. We're going to put in sample sizes 10, 25, 50, and 100. Okay, so we want to evaluate it at all these different sample sizes. This is something I would maybe do with my first level stats course, just to show them that we do get pretty good coverage even at small sample sizes using a t-interval if we know with some degree of certainty that our parent distribution is normally distributed. So we set mu, that's the true population mean, to 0. Well, an option within the R norm function is the mean, so we're going to set that to 0. We could have also set SD equal 1, which is also a option within the R norm function. And we get back this. So this is the proportion of times that the true mean was captured. So notice we're a little bit liberal here, a little bit less than 0.95, but otherwise we get very, very close once we get up to 25. Very easy. So we could apply SimT.ci to a normal, uniform, or gamma distribution. We could run them all just like this. So notice all that's changed here is the generating function. Okay, so we've got normal, uniform, gamma. The sample sizes are the same. The true means are going to vary based upon that default distribution. So for example, if we do min and max of 1, the mean for a uniform is 0.5. Okay. The mean for a gamma is going to be the multiplication of the alpha and beta for the gamma, so we get a 2. All right, so we can run all these. We can combine the results. So cbind is just going to take all of these results. So we'd see something like this for the normal, then something like that for the uniform, and then for the gamma. We're going to put it all together and report it out. Okay, so elapsed time and the min, and also all those results all together. All right, so that will cover everything for simulation, and something we'll practice in lab as well is this idea of writing a simulation function.